Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture number 11 in the course Introduction to Robotics. Today we'll be looking at velocity propagation from link to link and static forces. So when a robot manipulator moves, the velocity also moves from the base joint towards the end effector, and the forces propagate backwards from the end effector to the base joint. Now in the last class we looked at Jacobian, which gives us the relation between the joint velocities and the end effector velocities. Today we'll be looking at velocities and static forces, and then we'll move on to the study of dynamics, which actually shows us the relation between between motion and forces. So today's topic is velocity and static forces. So we start off by looking at linear velocities. So the first velocity we look at is a linear velocity. So a rigid body is moving with a linear velocity. How do we define that? So what we do is we first say that, say for example, a rigid body, okay, moving with a linear velocity. So how do we express this in terms of frames? So we have a fixed frame, which is my frame A, and I have a moving frame, which is frame B. So let's put it like this. This is my frame B, and which is moving, frame A, frame B, and there is a point QB, which is on frame B. Now the distance between the origins of these two frames is A, PB, ORG. We know what is the meaning of this, is the distance between the two frames. And when this body is moving with a linear velocity, the relationship, its relation with respect to frame A is given by VAQ is equal to AVB ORG plus the rotation matrix A BR into B into BQ. Okay, so the angle between the two frames A and B is given by the rotation matrix ABR. Now the velocity of the point expressed in frame A has two parts. It can be because of the change in velocity between the origin of the two frames, or it can be its own velocity, which is BVQ. Now we have to make the assumption that this rotation matrix is a constant. Otherwise it will not be a linear velocity. So rotation matrix not changing. Okay, so this rotation matrix that we know, okay, not changing with time. Okay, so this relationship gives us the relationship of the linear velocity. Now what about angular velocity? Now angular velocity is very important in robotics, because robot link serial arms, which are made up of revolute joints, they move, they rotate. Okay, all the joints are revolute, so they rotate, and this velocity propagates from one link to another link. So let's try to understand very clearly what is this rotational velocity. So this is a frame A, okay, which is not moving. So this is my frame A, which is not moving. Now there's a frame B, which is, this is my frame B, let's say. This is my frame B, which is given in black color, this frame B. Now this frame B is rotating about an axis with an angular velocity. Okay, so this is my frame B, and let's say there is an axis like this. Okay, and this is frame B is rotating, A omega B means frame B is rotating about this axis, which is on frame A, and the angular velocity is omega. So now if there is a point, let's say there is a point here which has coordinates BQ, the point is Q expressed in frame B. Now because frame B is rotating, what will happen? This will tend to take a circle like that. This will also tend to rotate like that. I hope you can understand, you can visualize that. Okay, because frame B, so the point Q is fixed in frame B, and frame B is rotating about this axis. So this point will start having a circular kind of motion like this. So if I draw it, enlarge the drawing here. So let me enlarge the drawing and draw it here. Okay, so this is the center of this circle. This circle I'm drawing it here. Now this is rotating about the axis. Now this is a point Q. This is my point Q at time t. If it is here, means it is there. Okay, this is my angle theta. Okay, now after some time, say del theta, the point will go there. This is exaggerated, but it is del t is very small instant of time. This is actually very small distance. Okay, so it will become qt plus del t. Now it has come here now. Now you can see from this figure that there is a straight line here like that. Okay, so this one we can say is del q, the amount by which it has changed. Now what is this distance? It has been rotating with an angular velocity a omega b. So this in small instant of time del t is equal to omega into del t, that you can understand, right? So this is the small angle by which it is subtending in there. Now what is the radius there? Radius is, this is q. Okay, this length is q, and this is theta. So this r is equal to q into sine theta. Okay, so what is this distance? This distance is equal to r into del theta. We know that for a circle. Okay, so this is my r, and this is my sorry, if this is my small angle del theta and the radius is r, then this distance arc is equal to r into del theta. That's what we are doing out here. So what we are getting is del q is equal to apq, okay, that is the distance q sine theta. Okay, that is q sine theta is the radius of that circle into a omega b into del t. Okay, so let me write it clearer. So a into omega b into del t. This is the angle subtended in the center. This is my angle. So it is r into del theta. This is r, and that is del theta. Okay, so that is the arc that it is subtending. Now, in order to find the velocity, the incremental velocity, we divide both sides by del t, and what this becomes, that we see it is a pq is equal to a omega b cross aq, right? So this is how we write the angular velocity. Okay, now so this gives us an expression for the angular velocity. Now the angular velocity is this one. Now this is an expression which is giving us the linear velocity, right? So so a body that is rotating, okay, with an angular velocity, what would happen is this point q will also be having a linear velocity, and that is exactly what we are seeing here, that we are able to get. So this is here. Okay, so now let us move on and look a little bit into angular velocities and how are they related to the rotation matrix. Now we have seen that the rotation matrix R is an orthonormal matrix. Okay, so this is an orthonormal matrix that we have seen when we derived the rotation matrix. So because it is an orthonormal matrix, we can write R into R transpose is equal to the antimatrix I. Okay, now if I take the derivative of the rotation matrix, then what we'll get is R dot into RT plus R into R dot T is equal to 0. This is what we are getting, and I can write this as R dot into RT plus R dot into RT transpose, the whole thing transpose. Okay, so if I take the whole thing transpose, what is going to happen is it will become R dot into R transpose, whole thing transpose. You'll get the same term here, R into R dot transpose. Okay, now what we see here, we can write this as S plus S rest is equal to 0. And what is S? S is a skew symmetric matrix. Okay. And S is equal to a skew symmetric matrix, and S is equal to R dot into R transpose. This is something we have seen. Okay. So what it basically means that R dot into R inverse is equal to a skew symmetric matrix S. Now, we can also derive the same thing by looking at the rotation matrix. Okay, so velocity of a point due to a rotating reference frame. So if we have a point A, okay, and we have A, B, R, so BP, this is something we have seen. AP is equal to the rotation matrix R into BP. So this is a point P, which is expressed in frame B. So this can be expressed in frame A by putting the rotation matrix. Okay. Now, if frame B is rotating, okay, then AP will be changing even when BP is constant, right? So because frame B is rotating, okay, then we can say that in order to find its velocity, I take the derivative AP dot is equal to A R dot B into BP. Okay. Now the frame BP will be fixed to frame B, right? So it will not have a velocity in frame B. So, or using the notation of velocity, we can write A VP is equal to ABR into BP. Okay. So what we are saying is that this, because of this frame B which is rotating, okay, this point P on B is going to have a linear velocity in frame A. And this linear velocity in frame A is written in the form A VP is equal to into ABR inverse into AP. So this part we get from here. So what is BP equal to? BP is equal to RB inverse into AP. Okay. So from here I get that. So this I put it in here. So in place of BP I put that in. And now if I open the matrices, what you see is that AVP is equal to AR dot B into ARB inverse is equal to transpose, so we get this into AP. Okay, this is what we are getting here, and we are seeing that this matrix R dot into R transpose is what we call S. So what we are seeing here is that AVP is equal to S into AP. So this basically means that this point this point which was in frame B can, and frame B is rotating with respect to frame A, will have an angular velocity which is given like this, which is related by this matrix R dot into R transpose, which is a skew symmetric matrix. Now the skew symmetric matrix is S is equal to 0 minus omega Z, omega Y, and here it is omega Z, 0 minus omega X, and here it is minus omega Y, omega X, and 0. Okay, this is the skew symmetric matrix R dot into R transpose. Okay, and we can this can be defined by a 3×1 column vector as omega is equal to omega X, omega Y, omega Z. Okay, and SP is equal to omega into P cross P. This is something we derived some time back also. Okay, so what we had derived some time back is this. Okay, so this is exactly what we are saying, omega cross AQ. So what is omega? Omega is a skew symmetric matrix which is given by this term. Okay, so this is the term that gives the skew symmetric matrix, and the skew symmetric matrix is related to the rotation matrix in this way. Okay, so this is something that we are seeing that is very interesting in terms of the rotation matrix, that the rotation matrix can also be used to find this skew symmetric matrix. Now this shows us that a body which is rotating, okay, will also have a linear velocity, and this would mean that in our manipulators, which are serial arms, in which the joints are revolute joints, all the rotations there are going to cause a linear velocity in the forward joint. Okay, so let's look at what we call the velocity propagation from link to link now. So velocity propagation from link to link, what does this mean? I have a manipulator like this, and there are revolute joints, and this is having an angular velocity theta1 dot, theta2 dot, theta3 dot. Okay. Now because there is an angular velocity here. This joint here will be subjected to an angular velocity and as well as a linear velocity. Okay, so this velocity will start propagating in this direction. So this link number 2 will have its own velocity, which is theta 2 dot, plus it's have the velocity of the previous joint, which is theta 1 dot. Okay, similarly, theta 2 dot will propagate forward, and this link will have velocity of the previous link plus its own velocity. Now this is very easy to understand. If you look at this example, so this is a two-link system, easier to understand. This is theta 1 dot, and this is rotating theta 2 dot. Okay, now because this link, the link number 2 is having theta 2 dot, and the previous link was having theta 1 dot, so the total velocity of this fellow will become theta 1 dot plus theta 2 dot. That means the velocities are moving in the forward direction now. Okay, so from the base link, the velocities will be going forward towards the nth link. Now let's look at a general case of velocity propagation from link to link. So this is a three-dimensional shape we are drawing just to explain that how velocities propagate from link to link. This is one link, and there is another link on this side, so it can have any shape. Okay, so this can have any shape. Now we have an axis, so this one axis here, and there's another axis there. So this is my axis zi, and this is my axis zi plus 1. Now let us say that this is the origin of my frame here, and that is the origin of the frame there, and there is, okay, let me not draw it here, let me draw it here. The same thing, but okay, it's easier to understand. Okay, so the origin is there, and I have a distance here now between the frames. That distance is pi plus 1. Okay, now there is an x coordinate, there's an x-axis xi, there is an xi this side also. So there is an xi on this side, xi plus 1 on this side also, and that is zi plus 1, this is zi. Okay, now this origin here is subjected to velocity omega I, okay, and vi. Let's say this axis here, which is this frame which is fitted here, is having an angular velocity omega I and a linear velocity vi. Okay, now the next frame, which is here, this is my next frame, that is subjected to omega I plus 1, okay, and vi plus 1. Okay, I hope you understand this. So this is basically the previous link, and that next link is there, which is the next frame. So if I consider a two-link manipulator like this is one frame, this is another one. Okay, so my z0, z1 is here, z2 is there. Okay, this is my x0, this is my x1. Okay, in terms of ds parameters. So what we are saying is that this is my first link. Okay, and this is the second link is this one. That is my second link. Okay, so there is a frame, the ith frame, and the next frame is the I plus 1th frame. That's what is being explained here. Now the ith frame has omega I and vi, and the I plus 1th frame has omega I plus 1 and vi plus 1, angular velocity and linear velocities. Now how would the velocities propagate in the forward direction? We have seen they go in the forward direction. So we are trying to express the velocity in the forward direction. The rotation matrix, please remember, when we are saying the rotation matrix relates a frame from the rotated frame to the reference frame. Okay, so let me draw the rotation matrix. You remember that, I'm sure, but I'll just write. So this is a point BP, okay, which has u, v, w, and the point has x, y, z in frame A. Okay, now the rotation matrix AP is equal to rotation matrix A to B into BP. That's my rotation matrix. Okay, so it is relating the coordinates of a point in a rotated system to that of the reference system, which is A. But in this case, we are seeing that we are expressing the velocity from frame I to frame I plus 1. So we're going the reverse direction. So it is going to be BP is going to be ARB inverse into AP. Okay, so please note this, we are going in the forward direction. This basically means it is going backward to the reference frame. Now, now we write it this way. So omega I plus 1, omega I plus 1. So what is the meaning of this way of writing? First is that it is omega I plus 1th frame. Okay, and it is expressed with reference to I plus 1th frame. Okay, this is the meaning of it, is equal to R into I plus 1 into I omega I plus theta I plus 1 dot. So theta I plus 1 dot is its own velocity, theta I plus 1 dot, that's its own velocity. So what we are saying is that the velocity of the next link, that is omega I plus 1, expressed in its own frame I plus 1, is on the left hand side, is equal to the velocity of the previous frame, that is omega I is the velocity of the previous frame, into the rotation matrix. This is the inverse, please note. Okay, so it is not I to I plus 1, it is I plus 1 to I. So it is the inverse or the transpose of this, plus its own velocity, which is theta I plus 1 dot. So this basically shows us how velocities propagate from one link to another link. This says that the next link will have its own velocity plus the velocity of the previous link, which is expressed in ith frame. So we have to multiply it with the rotation matrix, inverse of the rotation matrix, to get it in the I plus 1th frame. What about the linear velocities? The linear velocities Vi plus 1 expressed in I plus 1th frame is equal to R of I plus 1 into I. Okay, this is also the inverse, divided by VII, which is the velocity of the previous frame, plus omega I cross Vi plus 1. Okay, so what we're seeing is that because of the rotation, there is a linear velocity which is coming. So the next link, I plus 1th link, will be subjected to the velocity of the previous link, which is this linear velocity, which is this one, plus it has a linear velocity because of the rotation of the previous link, which is this one. Okay, so this one gives us the motion of the velocities in the forward direction, and this gives us the linear velocity motion in the forward direction. So these two equations we are going to use to find out how the velocities are moving from one frame to the other frame. Now let's look at a very simple example where we'll try and understand how these velocities are propagating from link to link. Now this is an example. This is a two-link manipulator. Okay, so there are two links here. So there is one link here and there is another link there. It's a two-link system. Now this is my x0, this is x1, as per DS notation x2, this is z2, this is z1. Okay, and this is the third frame, which is, let's call it x3 is that side, so x3 is that side, y3 is this side. Okay, why not? We need not draw the y's, but this is just for understanding. Okay, now the link lengths are L1 and L2. Okay, let's call the link lengths L1, L2, and the link angles is theta 1 and that is theta 2. Okay, that is my so it's a two-link manipulator, 2 degrees of freedom, planar. And now we are saying that the angular velocity of the first link is theta 1 dot and the angular velocity of the second link is theta 2 dot. Okay, so we want to know what is the velocity of the third frame, which is here now. So what is theta 3 dot and what is v3 dot v3? Okay, so what is the linear angular velocity of the third frame? I hope the question is clear. So now let's when we look at this, the frames that have been attached, we find that the first frame 0 to 1s frame has a rotation matrix which is cos 1 minus sin 1 0 0. So this is sin 1 cos 1 0 0, then it is 0 0 1 0, and then it is 0 0 0 and 1. This is always the same. We have seen whenever the two frames are together, 0 and 1. Now the second transformation matrix, which is relating the frame 2 to frame 1, is given by cos 2 minus sin 2 sin 2 cos 2. These are all rotations about z, so this is the way it appears. Okay, and the third one, please look at the third axis and the second axis. The z's are parallel, so the z's are parallel, the x's are in the same direction. Okay, so there is, because the x2 and x3 are in the same direction, what is happening here is that we are having the matrix 2 to 3 as 1 0 0 0 1 0 0 0 1, which is the identity matrix, and there is a shift only of L2 in the x direction. Okay, so if you look carefully at the frame 2, and the frame 3, what you'll find is x2 and z3 are in the same direction. Okay, so there is no rotation between them. So if there is no rotation between them, then it's an identity matrix. The rotation matrix is an identity matrix, and that is what is being shown here. Okay, so now let's start off. So first what we're trying to do is we are going to use these two equations. Please remember these two equations, which are very simple. So this is one equation which is very simple, and there is another equation. This one is also very, very simple. This one gives us the angular velocity, this gives us the linear velocity. What does this equation tell us? That the velocity, angular velocity, is equal to the velocity of the previous link plus its own velocity. So what we do is we proceed and say that omega 1 is equal to 0 0 theta 1 dot. So the frame 0 is a fixed frame. So frame 0 is fixed. So omega 0 is equal to 0. It's not moving, it's not rotating, right? It's a fixed frame. Okay, and hence the velocity of the first frame is its own velocity. There is no velocity which is coming from the previous frame, which is equal to 0 0 theta 1 dot. Okay, what is v1? Now we are saying v1, the origins of the two frames are the same, right? So there is no linear velocity there. They can move apart. Okay, so this is equal to v1 is equal to 0 0 0. So we see that the first axis has angular velocity and no linear velocities. Okay, now what about the next one? So the next one is here. So this point, the origin of frame 2 will have an angular velocity plus the frame 2 is going to have an angular velocity plus a linear velocity. Okay, why? Because the previous frame has a angular velocity of theta 1 dot. So let's look at the second case. So omega 2 is equal to 0 0 theta 1 dot plus theta 2 dot. Okay, so this is what we are getting here. Okay, so if you go back and look at the frames, okay, then what we are seeing is that the linear velocities, the angular velocity is going to be the sum of the previous angular velocity plus its own angular velocity, and this is what we have done. Okay, so we just added both of them. Now something to note here, what happened to r? Okay, because the angular velocity is about the z-axis in both the cases. Okay, please note that this is about z-axis. Okay, and yes, so this is about the z-axis. So both of them can be added, and there is no rotation matrix between them. Okay, because they are both rotating about the z-axis only. So that is why we don't put a rotation matrix there. Okay, now omega 2 is equal to this. What about v2? Now this is equal to r inverse, which is equal to c2 s2 minus s2 c2 0 0 1 0 0. This is 0 0 0, and into the angular velocity, which is equal to L1 theta 1 dot 0, which is equal to, what is this equal to? It is equal to L1 S2 theta 1 dot, and this is L1 C2 theta 1 dot and 0. Okay, let's go back and look at that again. So I'm taking the this velocities. So the velocity of the next link is equal to velocity of the previous link. Okay, velocity of link 1 was equal to 0, so there's no velocity, plus a velocity because of the rotation of the previous link. So omega I cross pi, that is what we have done. So omega I cross pi. Okay, so this part is omega I cross pi plus 1. Okay, and how do we do that? So what is omega I? Omega I is of the previous link, so it is equal. So I get the cross product ijk. So what is omega I? Omega I is 0 0 theta 1 dot. Okay, plus there is a distance of, what is the distance? This cross distance is about the x-axis, so it is an L1, so it is 0 0. Okay, so if I open this up, what do I get? Is equal to L1 theta 1 dot. Okay, so it is in the second term it is going to come, and it will be this into this minus that into that, so it is minus of minus makes it L1 theta 1 dot. Okay, so from here I get this term. Okay, now so if I multiply it out, this is what I get as my velocity, the linear velocity of frame 2. What about frame 3? Frame 3 is equal to the same velocity as frame 2. Why? Because frame 2 velocity is we have seen here is equal to 0 0 theta 1 dot plus theta 2 dot, and frame 3 does not have any velocity. It's a fixed frame. Okay, so it's equal to 0. So it is equal to this. Okay, which is equal to 0 0 theta 1 dot plus theta 2 dot. Okay, now what about the linear velocities? Now the linear velocity v33 is equal to what? Let's go back and look at that velocity equation again. So the linear velocity is equal to the velocity of the previous link plus this rotational velocity which is going to come. Okay, so what was the velocity of the previous link? So the velocity of the previous link, that is link 2, was equal to this term here. Okay, so it is going to be a rotation matrix. Now what will be the matrix? Now if you look at let's look at this one again. So if you look at axis 2 and axis 3, okay, it is an identity matrix. Okay, why? Because the axes are in the same direction. Okay, there is no rotation between them. So the rotation matrix is not there, and omega 3 is equal to just the cross product of the omega 2 cross pi. Okay, and if you do that, so omega 2 is given by this one, which is equal to L1 sine 2 theta 1 dot. This is equal to L1 cos 2 theta 1 dot plus L2 theta 1 dot plus theta 2 dot, and this is 0. Okay, so what was V3 equal to? If you are getting confused, then let's go back here and look at this. V3 is equal to the velocity of the previous link. So V3 will become equal to velocity of previous link. R is not there because identity matrix, so this is I, plus omega 2 cross pi. Okay, so velocity of the previous link plus the linear velocity because of the rotation of the previous link, and that is what we are getting here. So what we are getting here is V2 plus omega 2 cross pi plus 1. Okay, so V2 was equal to this one that we have seen, plus this is equal to this term now, exactly the same way how we have got. So if you see, it's exactly the same. Okay, so it's omega 2 cross pi. So what we can do is I j k, and what is omega 2? Omega 2 is equal to, about the z-axis it is theta 1 dot plus theta 2 dot. Okay, and this is L 0 0, that's 0 0. So if you do that, you get this term, and V2 is the previous term, so this plus this is equal to this. Okay, so this is how we are getting the propagation of velocities, both rotational velocity and linear velocity, from one frame to another frame. Okay, and it is very simple to understand. All we need to do is just look at these two equations, and we have seen logically we should understand where these two equations have come from. So what we see here is that if there is a revolute joint robotic system, okay, so we have a number of links and they are rotational links. So there is theta 1 dot, theta 2 dot, theta 3 dot, like that. So what is going to happen is all these thetas will start moving in that direction. What I mean is this velocity of the second link will become velocity of the previous link plus its own velocity. Similarly, that of the third link will become the velocity of the previous link, sum of the velocities of the previous links and its own velocity. And because this is rotating, we will also end up with a linear velocity which is moving now. Okay, so this is something important to understand, that in a revolute joint robotic system, the velocities propagate from one link to the other link. Now let's look at the concept of static forces. We have looked at velocity propagation. Now let's look at force propagation. But something interesting is that both of them move in different directions. So what do I mean is, suppose there is a force acting here. Okay, this force will cause a reaction force here. Okay, now this reaction force will cause a force here, and this will cause a force here and here and here. So the forces are moving like this now. So from the top, the forces move backwards, and in case of the velocity, the velocities move forward. Okay, so these are two interesting things of force propagation and velocity propagation. What it means is that this is something very fundamental and very important to understand, that in terms of dynamics, this is extremely important, that if you consider a tuning system like this, okay. Now, even if this link is not moving, if theta 2 dot is equal to 0, okay, it's not moving. But because this link is moving, theta 1 dot is there, this theta 1 dot will propagate and theta 2 dot will become equal to theta 1 dot, okay, even though its own velocity is 0, okay. So this means that in a dynamic system, each link affects the other link, okay, and they are all coupled in that way, okay, and that is what makes dynamics pretty difficult. Now let's look at our next topic, which is static forces. Okay, so we are looking at static forces, and again let's look at the generalized case, okay, of a link which is drawn here, and we have another link which is here. So this is one link and this is another link, okay, generalized case. So now we start off again the same way. This is my zi axis and this is my zi plus 1th axis. Now on this axis again we have our origin here, and the next fellow has origin there, so there is a distance. So let's call this pi plus 1. That's the distance between the origins of the two frames. Now on this frame, on the ith frame, let us say there is a force acting Fi and a moment acting Ni. So what is Fi? Fi is a force acting. It has three components, Fx, Fy and Fz. And Ni is a moment acting. Again, it has three components, Nx, Ny and Nz. So in short, we are writing Fi and Ni. Similarly, on the next link, on the next frame here, the I plus 1th frame, we have Ni plus 1 and Fi plus 1. Okay, again, the same logic. Okay, F has three components and N also has three components. Now, if we, for static equilibrium, okay, for static equilibrium, what we need is the forces in the xyz directions, the sum of the forces in the xyz directions must be equal to 0, the sum of the forces, and the sum of the moments also must be equal to 0 for equilibrium. Okay, now for that what we do is we write first the force balance equations. Fii is equal to Fi plus 1, Fi plus 1. Okay, so the force here, Fi, must be equal to the force which is on the other link, Fi plus 1. So Fi plus 1 will have a reaction on Fi, and if it's in equilibrium, then both of them have to be equal. Okay, otherwise there will be a resultant in some direction. Now we observe that I plus 1 and ith frames are different now. So I basically put a rotation matrix here, I to I plus 1. Okay. So Fi is equal to the rotation matrix which is relating I plus 1 to I now. Now we are moving in this direction, so it's not the inverse. And this is my next force, Fi plus 1. So this gives me the force equation. What about the moment equation? Ni is equal to R times I into I plus 1 into N of I plus 1, I plus 1. Okay, that means the moment Ni plus 1 is coming backward now into the rotation matrix, plus there is a moment which will be coming because of this cross Fi. Okay, now this will be a moment. Let me write it like this. So there is about this point there is a distance pi plus 1 and there is a force Fi acting there. So it is Fi cross of pi plus 1. So it is an rotation matrix into I plus 1 into Fi plus 1, I plus 1. Okay. So what I'm trying to explain is that if there is a force here, Fi plus 1, and there is a distance pi plus 1, then this will cause a moment about this point here now. So this is my ith axis. Okay, this is the ith axis, and that is my I plus 1th axis, which is shown there. Okay, so this Fi plus 1 will cause a moment about the ith axis, which is being coming here. Okay, so pi cross r, because F is expressed in I plus 1th frame, so you have to multiply with the rotation matrix is equal to this. Okay, this is what it is saying. Now, if you observe that this term is equal to this term, okay, so I can simplify it and write Ni is equal to R times I into I plus 1 into N I plus 1 N, I plus 1 N into I plus 1. This is the moment, okay, of which is coming back, plus pi plus 1. Now this r times fi plus 1, I'm simply writing it as fi from the previous equation. Okay, and this is plus. So we have two equations here. The first equation is the force equation. So this is my force equation, okay, which is relating the force of the previous link to that of the next link. Okay, so the forces are moving in the reverse direction. So I plus 1th link force is having an effect on the ith link. Okay, for velocity it was just the reverse. Now what about the moments? The moment is here. Okay, moment is equal to this. So the n plus 1th moment multiplied by the rotation matrix is affecting the ith moment. Sorry, the moment on the ith joint, and there is an additional moment because of the force which is acting on the I plus 1th joint. Okay, so now this two relation again gives us the propagation of forces. But now if you look at the propagation of forces, it is moving in the reverse direction as compared to velocities. So it is coming from the I plus 1th frame to the ith frame. Now let's look at a very simple example again. Okay, so this is a very simple example. Let's try and solve this and see how forces propagate from one link to another link, because this is something that we are going to need when we are going to study our dynamics. In dynamics, velocities propagate, forces propagate, and each link affects the other one. So let us look at this. So this is the problem. Okay, so this is a two-link manipulator again. Okay, and this is my torque tau 1, this is torque tau 2, and this is my third frame x3, this is my third frame, this is my y3. Okay, and there is a force acting there which is F3. Okay, no moment. So N3 is equal to 0 and force F3 is acting at that point. Now this force F3 has components Fx, okay, Fy and 0. Okay, so the force which is acting at the end effector or at the end and the tip is acting on frame 3. Okay, that is something to note, and it has Fx, Fy and 0 because it's a planar system. Okay, so that is the force which is acting on the origin of frame 3. Now there is no moment acting, so N3 is equal to 0. Okay, now what are we going to do is we have to find the force acting on the second link and then the force on the the second joint and then on the first joint. So we go back to our two equations. Okay, so the first we are going, for force we are going to use this equation, and for moment we are going to use this equation. Okay, so we systematically just look at those equations and put in the values, and then you have your solution. Okay, so now force we have found. So what is the force 2? Force on joint 2, which is here. What is the force acting there? Is equal to Fx, Fy and 0. Okay, why? Because whatever force is acting here, this is a solid rigid link, right? So whatever force is acting at the origin of link of frame 3 will also be the same as that of frame 2, because it's a rigid link. It will just and it's in equilibrium, so they have to be equal. Okay, and there is no rotation matrix between them, right? So this is something we saw in the previous example also, that if you're say for example we saw here, so in the link of this nature, okay, the x's are in the same direction, x2 and x3 are in the same direction, z's are parallel, and this is a rigid body, so there is no relative motion between frame 3 and frame 2. Okay, so similarly here also it is the same, and what we do is we simply write our F2 is equal to Fx, Fy and 0. What about N2? Now the moment is equal to the moment of the previous link. Now N3 was equal to 0, so N3 is not coming into picture, into so N3 into our I into I plus 1 plus Pi plus 1, which is equal to L2 in the x direction. So this means in the x direction. So L2 is the distance in the x direction cross Fi, so Fx, Fy and 0. Okay, so the moment is equal to the moment of the previous link, which is equal to 0 because N3 is 0, plus the moment because of a force which is acting at the origin of the third frame, So that is equal to L2 is the distance, x is in the direction of x, cross of fx fy, which is this one now. Okay, so what we do is we can simply find this out and say N2 is equal to, if you multiply it out, ijk again, we get L2 fy, and this is the force, this is the moment acting about the z-axis. Now if I just draw this link, this link, if I draw it here, okay, I'm drawing this link here just to understand. Okay, so this is my x-axis, this is my y-axis, this is y3. Okay, and there is a force acting on this, which is fx, fy, and 0. Okay, so what will be the force acting on this point here? So it will be exactly the same, because otherwise it will not be in equilibrium, right? So the forces acting would be the same on this point and this point. Okay, but this force here, okay, is going to cause a moment about this point. Okay, so there is an fx, fy acting. Now the fx, let me draw it here, fx, fy, and fz. So the fx is along x and fy is along y. Now the fx is going to go straight through, so it will not cause a moment. This cannot cause any moment. Fy is going to cause a moment. Now Fy is this force in the y direction, and the distance is L2. So what will be the moment? It will be L2 into Fy. Okay, about which axis? About z axis. Okay. So if we just look at this carefully, we can also understand why it is happening like this. So the cross product is saying it is L2 cross Fx Fy, and this is the answer. Okay. So now let's look at the first case. So from third it has gone to second, from second it has gone to first, so F11 is equal to, now what is F11? There is a rotation matrix now. Now there is a rotation between the first axis and the second axis. So let me draw the, so this is Z0, Z1, this is Z2, this is Z3. Okay, and this one is my X0, this is X1, that is X2. Okay, so now when we are coming to frame 1, we see that there is a rotation between frame 1 and frame 2 now. Okay, so our rotation matrix will come in there, and this is equal to C2 minus sine 2 0 0 1, and this is S2 sine 2 0 0 1, this into Fx Fy 0. Okay, so we are using the equation again. Just to go back, we are just simply using this equation. Okay, so we are using this equation, rotation matrix into the previous force. Okay, and if we do this, then what do we get is F1. We just need to multiply it out. We get C2 Fx minus S2 Fy, S2 Fx plus C2 Fy, and 0. Okay, now we have to find the moments coming on the first axis. So the moment which is coming on the first axis is the moment which is coming from the forward axis. From N2 moment will come. So what was the N2 moment? N2 moment was 0 0 L2 Fy. Okay, so we are going to get 0 0, the moment coming from the forward link, L2 Fy. Okay, plus again there is a force which is acting on axis on the origin of 2, which is going to cause a moment. So which is this L1 into cross Fy. Okay, now this is because of this. This is because there is a force acting on the origin of frame 2 now. Okay, so this will cause a force. This will cause a moment on frame 1. Now if I open it up, what do we get? What we get is this one. So 0 0 L1 S2 Fx plus L1 C2 Fy plus L2 Fy. Okay, so this much is the new component. This is coming from the previous one. Okay, so the total moment which is acting on the manipulator on joint number 1 is given by this expression. Now if I write it in terms of the moments which are acting on joint 1 and joint 2, we can write it as tau 1 is equal to L1 sine 2 Fx plus L2 plus L1 C2 into Fy. Okay, and tau 2 is equal to L2 into Fy. Now something very, very important to note here is that there is an Fx and there is an Fy. Okay, and there is an Fy here, there is no Fx here. In the second joint there is no Fx. So if I write it in matrix form, I can write it as tau is equal to L1 sine 2, and on the other side we have L2 plus L1 cos 2. This is 0, this is L2, and this is my Fx Fy. Okay. Now, so how did we get that? I simply took Fx Fy outside, and we write it in matrix form. Okay. Now this is also called the Jacobian. This is also called the Jacobian. Now, is this Jacobian the same as the Jacobian which we did in the last class? Okay, they look different, right? It's a 2 by 2, both are 2 by 2, but they look very different. Now, this Jacobian is expressed in frame 3. This is in frame. Why is it in frame 3? Because my force that I applied was in frame 3. So if you note here, this force F3 is in frame 3. So the answer that we are getting is all in frame 3 actually. So I need to convert it into frame 1. So you can convert this Jacobian can be converted to frame 1. How would you do that? By multiplying with their rotation matrices. Okay, so by using the rotation matrices, you can convert the Jacobian in frame 3 to frame 1. Or sorry, not frame 1, but frame 0, on the 0 reference frame. Then you'll find both the Jacobians are the same. So the J3 in 0 frame is equal to the rotation matrix 0 to 1, 2 to 1 to 2, and 2 to 3 into Jacobian into frame 3. Okay, so if you do that, we see that the Jacobian also relates not only the velocities, it also relates the forces which are acting at the end effector. And now let's look at this proof, a very simple kind of proof here, where we have a link and we have a force acting. There is some force acting here, and there's a joint torque tau. Now we know that from a virtual work principle from the principle of virtual work, we know that this force will cause a very small displacement del x here. Okay, and because of this force there will be a torque, and this torque will have a very small displacement del theta. And then we know that F into del x must be equal to tau into del theta from virtual work. So what we are saying is this force is causing a very small displacement, and this moment is also causing a very small displacement, and F dot del x is equal to tau into del theta. Okay, and now if I write it like this, F transpose, because it is Ft into del x, okay, because these are matrices, into tau into, I can write it like this. Okay, now we know that del x is equal to j into del theta. This is from our Jacobian that we derived. Okay, so if I take this and put it here, then it becomes F transpose into j into del theta is equal to into del theta. Okay, now what we can do is we can cancel this side and this side. So we get F transpose sorry, this is F, this is j into, yeah, this is j. So now what we are getting is F transpose into j is equal to tau transpose. So if we take transpose of both sides, then what we get is tau is equal to j transpose into F. Okay, taking transpose of both sides. So this is a very, very important result, which tells us that the joint torque is equal to the Jacobian transpose into the force acting at the end effector. Okay, so the Jacobian not only relates velocities, so something to remember very, very carefully here is that the Jacobian relates joint and end effector velocities. This is one, but the Jacobian also relates the end effector force and joint torques. Okay, Now this is two most very important things to remember. So if you have a manipulator like this, and there is a joint torque which is acting here, so there is some force acting here, a force moment acting here, okay, then this force moment is going to have effects on is going to cause torques on the joints now, okay, and that tau is equal to J transpose into F, okay. So we can get the the torques at the joints due to a force acting at the end effector simply by multiplying it with the transpose of the Jacobian. But be careful that this Jacobian is in third frame. It is not in zero frame. But you can convert it to, you can very easily convert that into the zeroth frame. So today we looked at the velocity propagation from one link to another link, and we also saw how the forces move from the end effector to the base link. And in the next class, what we'll be doing is we'll have to move on slowly to the study of dynamics that gives us the relation between forces and moments acting on the joints and their effect on the joint torques. Okay, so we will stop here today and we will continue in the next class. Thank you.